What is stoichiometry? This word is derived from two Greek words, stoichion and metry. Stoichion means elements and metry means to measure. So stoichiometry literally means to measure what? The amounts or quantities of elements. That is the literal meaning of stoichiometry. Though it means to measure amounts, under stoichiometry we often calculate the amounts of reactants and products involved in a chemical reaction. I hope you know the difference between measurement and calculation. Measurement is done using a measuring device. To do that, sometimes you may have to go to a laboratory and conduct an experiment. But calculation is done in the comfort of your home or sitting at your desk. So, in stoichiometry, we often calculate the quantities or amounts of reactants and products involved in a chemical reaction. How do we do that? That's what we are going to discuss in this video. Now, hematite is a mineral or ore of the metal iron found in nature. From this ore, iron can be extracted by reducing it with carbon monoxide in a blast furnace. We shall worry about what a blast furnace is some other time, but understand that by carrying out a chemical reaction between these two, iron can be extracted. Now my question is, how much hematite should I buy to extract 10 tons of iron by using this process? This is a valid question, right? And I want to figure this out without stepping into a laboratory. How can I do that? Now, to be able to do this, we developed a system. Now, what is this system? In this system, we assigned symbols for all the elements and we experimentally determined the formulae of all the compounds. And we use these symbols and formulae to represent the elements and compounds involved in a chemical reaction. And the symbol we assigned for iron is Fe. And someone experimentally found that hematite is an ionic compound of iron and oxygen. The symbol for oxygen is O. And it was also experimentally found that in each unit of hematite, there are 2 iron atoms and 3 oxygen atoms. And that information is shown as subscripts to the symbols. And this whole thing is what is called as the formula of that compound. And all this information was obtained experimentally. Someone did the hard work for us and we are just using this information. So hematite ore is ferric oxide and its formula is Fe2O3. Similarly, someone found that the molecular formula of carbon monoxide is CO. Now, let us represent this chemical reaction using symbols and formulae. Now, the substances that are getting consumed or disappearing during a chemical reaction are known as reactants, and the substances that are getting formed or appearing are known as products. And we always draw an arrow from the reactants to the products to indicate that these substances are getting converted into these substances. And in this reaction, what are the reactants? You must be able to identify them. Here, one of the reactant is hematite ore, that is ferric oxide, and if you want to represent it using its formula, that is Fe2O3. And the other reactant is carbon monoxide and its formula is CO. So let us represent carbon monoxide by its formula. To indicate that these two are reacting with one another, we show a plus sign between them. Now we have to draw our arrow and we have to show the products to the right of this arrow. And one of the product in this reaction is iron, and we have to represent it by using its symbol, that is Fe. And experimentally we found that another substance that is formed during this reaction is carbon dioxide. And this is the formula of carbon dioxide, so we can represent it by using its formula CO2. So here we represented all the reactants and all the products involved in this chemical reaction using their symbols and formulae. And this is what we call a chemical equation. In a chemical equation, the substances involved in the chemical reaction are represented by their symbols and formulae. Now, what is the purpose of writing a chemical equation? See, one obvious use of a chemical equation is, by looking at it, we can easily figure out the various reactants and products of that reaction. You don't have to read through this sentence to figure that out. We can easily understand that from this equation. So obviously, a chemical equation is a symbolic representation of the chemical reaction. But is it just a symbolic representation or is it more than that? Let us see. See, the symbols and formulae that we use in a chemical equation not only tell us what they are, but they also represent one unit of that substance. That is one chemical unit of that substance. What is a chemical unit of a substance? It is the smallest amount of that substance that you can have. What is the smallest amount of iron that you can ever have? Is one iron atom, right? Anything smaller than that is not iron. So the smallest amount of iron you can have is one iron atom. So that is the chemical unit of iron. Iron is composed of iron atoms, separate iron atoms. Similarly, what is the chemical unit of carbon dioxide? The smallest amount of carbon dioxide you can have is one molecule of carbon dioxide. Anything smaller than that is not carbon dioxide. So the chemical unit in this case is one molecule. So in this case, this formula CO2 not only tells me that it is carbon dioxide, but it also represents exactly one molecule of carbon dioxide. Here Fe not only tells that it is iron, it also represents exactly one atom of iron. And same in these two cases. Here it represents one molecule of carbon monoxide. Here one formula unit of ferric oxide. So these symbols also represent certain amount of that substance. And to indicate clearly that this symbol represents one atom, you may put that number 1 before that symbol. You can even write it like this. So 1 Fe obviously means one atom of iron. And if you want to represent two iron atoms, you have to put the number 2 before it. Now, by convention, if that number is 1, if you are only representing one atom, you can omit this one. So, if you don't see any number before a symbol, understand that there is a 1 there. That is implied. Now, what is the symbol of oxygen? It is O. And this symbol represents obviously one atom of oxygen. But oxygen is generally composed of oxygen molecules, and in each oxygen molecule there are two oxygen atoms, and these two oxygen atoms are bonded to one another. They are glued to one another. So how do you represent oxygen molecule? Because there are two oxygen atoms here, you may be tempted to write it as 2O. But that is not correct. To indicate that in oxygen molecule there are two oxygen atoms that are not independent and that are bonded to one another, we have to put that 2 as a subscript to this symbol. So the correct representation of an oxygen molecule is O2. So this tells me that you are talking about an oxygen molecule that is composed of two oxygen atoms that are bonded to one another. But for any reason, if you have to represent two separate oxygen atoms that are not bonded to one another, then you have to represent it by 2O. So 2O and O2 do not mean the same. O2 means one molecule of oxygen in which two oxygen atoms are bonded to one another. 2O means two separate independent oxygen atoms. So pay attention to this. Now let us use this knowledge to read this equation again. If there is no number before a formula or a symbol, that means there is a 1 there, right? So let us explicitly show that number for the sake of our discussion. Now this means one formula unit or chemical unit of ferric oxide reacts with one chemical unit of carbon monoxide to form one chemical unit of iron and one chemical unit of carbon dioxide. And in one unit of ferric oxide, there are two iron atoms and three oxygen atoms. In this unit, there is one carbon atom and one oxygen atom. Here we have only one iron atom. Here we have one carbon atom and two oxygen atoms. Now, if you compare the atoms of each type on both sides, on the side of the reactants and products, you would notice that here we have two iron atoms, but only one iron atom here. Here we have 3 plus 1, 4 oxygen atoms, but here we have only 2 oxygen atoms. Of course, we have one carbon atom each on both sides. So by looking at these numbers, it appears that some iron atoms and oxygen atoms are getting lost during this reaction. That is, they are getting destroyed or disappearing during this chemical reaction. And you know, atoms have mass. If atoms are getting lost, that means mass is getting lost or destroyed. So it appears as if some mass is getting destroyed during this reaction. But that cannot happen. That is impossible. Why? Law of conservation of mass, right? Lavoisier. That is, mass can neither be created nor destroyed during a chemical reaction. The total mass of the reactants must be equal to the total mass of the products. Now, some of you might say that maybe some iron atoms are getting converted into atoms of some other element that you have not shown in the equation. First thing is, I have shown every reactant and product involved in this reaction. I already told that. I am not missing anything here. And secondly, during a chemical reaction, atoms of one element cannot be converted into atoms of some other element. That is called transmutation, and transmutation cannot take place during a chemical reaction. Impossible. So that means during a chemical reaction, the total number of atoms of each element must be same before and after the reaction. Obviously, right? You cannot change an iron atom into an oxygen atom during a chemical reaction. So that simply means atoms of each type must be same before and after the chemical reaction. In other words, atoms of each type must be conserved. If atoms are conserved, that means mass must also be conserved. Right? So, we have a problem with this equation. And that problem is, this equation violates law of conservation of mass. So we have to correct this equation so that law of conservation of mass is not violated. How do you do that? So we have to correct this equation for two reasons. One is that law of conservation of mass cannot be violated during a chemical reaction. Secondly, there is no transmutation of atoms during a chemical reaction. That is, you cannot change atoms of one element into atoms of a different element during a chemical reaction. Now, what should I do to satisfy these two conditions? Simple. You just make sure that the total number of atoms of each element are the same before and after the reaction. Now, how do I correct this equation to make sure the number of atoms of each element are the same on both sides of this equation? By the way, this process is called balancing a chemical equation. Balancing a chemical equation is applying these two conditions to a chemical equation: law of conservation of mass and the fact that atoms cannot be transmutated during a chemical reaction. Here I am going to do it by trial and error. Let us start with iron atoms. On the reactant side there are two iron atoms, but on the product side there is only one iron atom. So to equalize them, can I put a 2 here? Now you have two iron atoms here and two iron atoms here as well. No, you cannot do that. Fe2 means a molecule of iron in which two iron atoms are bonded to one another. But iron does not contain any molecules. It contains only independent iron atoms. Therefore, you cannot change the subscript of iron here to equalize the number of atoms. Then what should you do? You can only change the number before the symbol. In this case, you can put a 2 before the symbol Fe. 2 Fe means two separate iron atoms. Now we have two iron atoms on the right hand side and two iron atoms on the left hand side also. So we are good. So remember, never change subscripts while balancing a chemical equation. By doing that, you are changing the nature of that substance, right? So never change subscripts while balancing a chemical equation. To balance a chemical equation, you can only change the numbers before the symbols and formulae. These numbers are also known as coefficients. So you can only change the coefficients of a chemical equation to balance it. Never change the subscripts. Now what about carbon atoms? There is only one carbon atom on each side, so we are good. What about oxygen atoms? On the reactant side we have a total of 4 oxygen atoms, but here we have only 2 oxygen atoms. So can I change this subscript to 4 and call it CO4? No, there is no compound with this formula. So you cannot change the subscript. Only you can change the coefficient. Now what should I put here? To equate the number of oxygen atoms, I can put a 2 here. Then oxygen atoms are good, 4 on each side. But now I have 2 carbon atoms here. See, this coefficient applies to each symbol in that formula. So now we have 2 carbon atoms here, but only 1 carbon atom here. So for that, if I put a 2 here, then the carbon atoms are good, but oxygen atoms are out of balance again. 3 plus 2 here, right? 5, but only 4 here. So this is not working. So I have to pick some other number. Let me try 3 here. Then I have 3 carbon atoms here. So to equalize the number of carbon atoms, let me put a 3 here as well. Now I have the same number of carbon atoms on both sides. What about oxygen atoms? Here I have 3 times 2, 6 oxygen atoms. Here I have 3 oxygen atoms. Here 3 times 1, 3 plus 3, 6. So we are good. So now we have balanced atoms of all types: iron atoms, oxygen atoms, and carbon atoms. And such an equation is called a balanced chemical equation. Now let us write down the balanced chemical equation here. Now I am going to omit this one. If it is a 1, I don't have to write it. So Fe2O3 plus 3CO 2Fe plus 3CO2. Now the coefficient you see before the symbol or formula is known as the stoichiometric number of that substance. And all these coefficients put together are known as stoichiometric coefficients. Now, what do these stoichiometric coefficients tell us? They tell a relationship between the amounts of these substances. These coefficients establish a relationship between the amounts of reactants and products, and it is these stoichiometric coefficients or this relationship that we use to calculate the quantities of reactants and products in stoichiometry. That's what we are going to do. Now, how did we balance this equation? First of all, why did we balance this equation? to apply these two conditions. Now, how did I apply these two conditions? By making sure that atoms of each element are the same on both sides of this equation. That means I made sure that atoms are conserved during a chemical reaction. Otherwise, I do not know how to apply these two conditions. I could satisfy these two conditions while balancing this equation only by making sure that atoms of each element are the same before and after the reaction. That is called conservation of atoms. That is, atoms are neither created nor destroyed during a chemical reaction. Sometimes this is also called as principle of atom conservation, abbreviated as POAC. So we used POAC to balance the chemical equation. That is conservation of atoms. So what is balancing of a chemical equation? It is applying these two conditions, that is law of conservation of mass and the fact that atoms cannot be transmuted during a chemical reaction. And how do you apply these two conditions to a chemical equation? By using principle of atom conservation. That is, atoms of each element must be the same before and after the chemical reaction. That is, atoms are neither created nor destroyed nor transmuted during a chemical reaction. Now let us read this equation again. What does it say now? It says 1 formula unit of ferric oxide combines with 3 molecules of carbon monoxide to produce 2 atoms of iron plus 3 molecules of carbon dioxide. So now we have a relationship between these formula units in this reaction, and using this relation we are going to calculate the quantities or amounts. Now this is called the molecular interpretation of the balanced chemical equation. Now this does not mean that every time you want to carry out this reaction you have to take only 1 formula unit of ferric oxide and 3 molecules of carbon monoxide. That does not make sense. Then what do these coefficients mean? These coefficients give us the ratio or the relative number of chemical units of each substance involved in the chemical reaction. This means for every formula unit of ferric oxide that you took, there must be 3 molecules of carbon monoxide, and in that process you will always get 2 atoms of iron and 3 molecules of carbon dioxide. So that is the relationship these stoichiometric coefficients tell us. Now we can treat this chemical equation like a mathematical equation. Now we can treat this equation like a mathematical equation and multiply all the terms with the same number without causing any imbalance in the equation. Now let us multiply each term in this equation with Avogadro's constant. Then 1 times Avogadro's constant formula units of ferric oxide plus you have to multiply each term with Avogadro's constant. So 3 times Avogadro's constant of molecules of carbon monoxide produce 2 times Avogadro's constant of atoms of iron plus 3 times Avogadro's constant of molecules of CO2. I can do this, right? I multiplied all the terms with the same number or the same constant. Now, if you have an Avogadro's number of particles, then that substance is 1 mole, right? So I can replace Avogadro's constant of formula units of Fe2O3 with 1 mole of ferric oxide. So 1 times 1 mole of ferric oxide, that is simply 1 mole of ferric oxide plus again this is 1 mole of carbon monoxide multiplied with 3 is 3 mole of carbon monoxide produce 2 mole of iron atoms to be precise plus 3 mole of CO2. This is interesting, right? Now we have another interpretation of the same equation in terms of moles. Now read this. It says 1 mole of ferric oxide reacts completely with 3 moles of carbon monoxide to produce 2 moles of iron and 3 moles of carbon dioxide. If you look at the coefficients, they are again 1, 3, 2, 3. So the stoichiometric coefficients are still the same. So we have the same stoichiometric coefficients here as well as here. That is in molecular interpretation and in this interpretation as well. This is called molar interpretation. Okay, so these stoichiometric coefficients not only give the relation between the number of chemical units involved in the reaction of various substances, it also gives a relation between the number of moles of various substances involved in that chemical reaction, and they are the same, right? Once I know the relationship between the number of moles, I can figure out the relationship between their masses, right? You know how to figure out the mass of 1 mole of ferric oxide. And you can do that for every other substance in this reaction. So once you have the molar interpretation, then you know how to convert that interpretation into masses, which is called mass interpretation. Now let us write down the mass interpretation. You know how to figure out the mass of 1 mole of ferric oxide. It comes to be around 160.0 grams. So 160.0 grams of ferric oxide combines with 3 moles of carbon monoxide. So 3 times 1 mole of carbon monoxide weighs approximately 28.0 grams. So 3 times 28.0 grams of carbon monoxide. These two combine to produce 2 moles of iron, that is 2 times 56.0 grams of iron, plus 3 times 1 mole of carbon dioxide weighs approximately 44.0 grams. See, now we have a relationship between their masses, and masses are something that we can measure. So by using the relationship between their masses, we will be able to answer our question. So how much ore should I buy to extract so many tons of iron, right? So I assume they are metric tons, so 10 times 1000 kilograms is 1 ton, and 1 kilogram has 1000 grams, so it would be so many grams. It would be 10 to the power of 7 grams. Now how do we figure out the mass of ore? Is nothing but ferric oxide, so we have to figure out the mass of ferric oxide from this relationship. How do we do that? See, to get 2 times 56 grams of iron, we have to take 160 grams of ferric oxide. But we want 10 to the power of 7 grams of iron. So how much ferric oxide should I take? So this relationship between their masses is what we are using to calculate the mass of ore that we should buy to get this much of iron, just by using a balanced chemical equation without stepping into a laboratory. Now let us consolidate our understanding with the help of another example. In the early 20th century, a German chemist by name Fritz Haber developed a process in which ammonia can be synthesized from nitrogen and hydrogen. This single chemical reaction revolutionized agriculture and food industry across the world. What is the chemical reaction here? As it says, we are synthesizing ammonia from nitrogen and hydrogen. Synthesis means preparing a compound directly from its elements. Now, how do you write a chemical equation for this? Simple. Identify what the reactants are and what the product is. Now here the reactants are nitrogen and hydrogen, and nitrogen is represented by its molecular formula N2, and hydrogen is represented by its molecular formula H2, and ammonia has the molecular formula of NH3. Again, this equation is not balanced. We have to apply law of conservation of mass and the fact that atoms cannot be transmuted during a chemical reaction. To do that, you have to equalize the number of atoms of each element on both sides. Here we have 2 nitrogen atoms, but there is only 1 nitrogen atom here. The subscript here is 1, and also the coefficient is 1 if there is nothing. So to equate the number of nitrogen atoms, I have to put a 2 here. Then what happens? There are 6 hydrogen atoms here, but only 2 here, so I can simply put a 3 here to balance this equation. Now both nitrogen and hydrogen atoms are balanced. So this is a balanced chemical equation. Now here nitrogen is a gas, hydrogen is also a gas, the ammonia formed is also a gas under those conditions. Now what is the molecular interpretation? it says one molecule of nitrogen combines with 3 molecules of hydrogen to produce 2 molecules of ammonia. That is what these stoichiometric coefficients tell us. So they give a relationship between the number of molecules of the reactants and products that are involved in the reaction. So the ratio is 1 to 3 to 2. So for each molecule of nitrogen, you must have 3 molecules of hydrogen, and in that process you will get 2 molecules of ammonia. Then what is the molar interpretation? These coefficients also represent the relative number of moles of the reactants and products. So we can simply say 1 mole of nitrogen reacts with 3 mole hydrogen to produce 2 mole ammonia. Now, what is the mass representation? You know, 1 mole of nitrogen is approximately 28 grams. So 28.0 grams of nitrogen reacts with 3 times 3 moles, right? 3 times 1 mole, and 1 mole of hydrogen is approximately 2 grams. So 3 times 2.0 grams of hydrogen. These two combine to produce 2 times 1 mole of ammonia. 1 mole of ammonia weighs approximately 17 grams. So now you have a relationship between their masses. And using this relationship, you can figure out the mass of nitrogen and hydrogen that you must take, say, to produce 500 kilograms of ammonia. You can figure out the mass of hydrogen by using this relationship. You can figure out the mass of nitrogen by using this relationship. Now, nitrogen, hydrogen and ammonia are all gases under the conditions this reaction is carried out. And in case of gases, we have a special law called Avogadro's law that states at a particular temperature and pressure, if you take equal volumes of different gases, then they must contain equal number of molecules, right? Now, if you have equal number of molecules, then you must have equal number of moles, right? To get the number of moles, you have to divide the number of molecules with Avogadro's number. So if numerator and denominator are same in all the 3 cases, then they must all have the same value. Then the converse also must be true, right? If you take equal moles of different gases, then they must all have the same volume at the same temperature and pressure. So, at a particular temperature and pressure, let us say 1 mole of nitrogen has a volume of V liters. Then 1 mole of hydrogen also would have a volume of V liters according to Avogadro's law. Because we have 3 moles here, we have to multiply that with 3. And again, 1 mole of ammonia at the same temperature and pressure will have the same volume of V liters, but you have to multiply it with 2 because we have 2 moles of ammonia in this representation, right? Now, if you look at the ratio of their volumes, it is again 1 to 3 to 2, same as the stoichiometric ratio, same as the ratio of their number of molecules, same as the ratio of their number of moles. So that means these stoichiometric coefficients in case of gaseous reactants and products also give the ratio of their volumes, right? So this is the volume relationship, and this is applicable only in case of gases. So from the balanced equation, we can derive all these relationships, and from these relationships, we can do stoichiometric calculations. Remember, this last one is only for gaseous reactants and products. So by looking at this balanced equation, I can say that one molecule of nitrogen reacts with 3 molecules of hydrogen to produce 2 molecules of ammonia. I can also say 1 mole of nitrogen combines with 3 moles of hydrogen to produce 2 moles of ammonia. I can also say 28 grams of nitrogen reacts with 6 grams of hydrogen to produce 34 grams of ammonia. And because these are all gases, I can also say that 1 volume of nitrogen combines with 3 volumes of hydrogen to produce 2 volumes of ammonia. Now finally, what are all conserved in a chemical reaction? Total mass is conserved? Yes. Mass of each element is conserved? Yes. Total number of atoms are conserved? Yes. Atoms of each element are conserved? Yes. Then a little later we would also understand that electric charge is also conserved when we deal with chemical reactions involving ions, and there interestingly we use this principle to balance the chemical reactions. And what is not conserved in a chemical reaction? Total volume may not be conserved. Here the total volume of the reactants is 4 liters, but the total volume of the product produced is only 2 liters. And total number of moles may not be conserved, because look at the total number of moles of reactants, 1 plus 3, 4, but the total number of products, moles of product formed is only 2. So they may not be conserved. Now let us work out some simple examples to end this video. Now what do we have here? Nitric acid is manufactured in Ostwald's process. That is correct. In this process, nitrogen dioxide reacts with water, and we are given the balanced chemical equation for that reaction. That makes our life easier. And we have to calculate the mass of nitric acid produced from 23 grams of nitrogen dioxide. So we are given the mass of nitrogen dioxide. We have to figure out the mass of nitric acid. Can we answer this question? I think we can, provided we know how to obtain a relation between the mass of nitrogen dioxide and nitric acid using this equation. If we can do that, we can answer this question. Now let us write down that equation again. 3NO2 plus H2O produce 2HNO3 plus NO. Now let us write the molar interpretation. If you want, you can write the molar interpretation for all the reactants and products. Nothing wrong in it. But because I am interested only in a relationship between these two, to answer this question, I am going to write an interpretation, a molar interpretation only for these two. And that says 3 mole of nitrogen dioxide will produce 2 mole of HNO3, of course, upon reaction with water. And I am omitting that part because I don't need it for my calculation. Now what is the mass of, this is molar interpretation, right? Now what is the mass interpretation? What is the mass of 1 mole of nitrogen dioxide? 14 plus 32, right? Is it 46? Yeah. So 3 times 46.0 grams of NO2 would produce 2 times, what is the mass of 1 mole of nitric acid? 1 plus 14 plus 48. Is it 12 plus 1? 13. 4 plus 1, 6, 63. So 63.0 grams of nitric acid. So we got a relationship between their masses using this balanced equation. That says if you had so many grams of nitrogen dioxide, you would have got so many grams of nitric acid. But here you have only 23.0 grams of nitrogen dioxide. Then how much nitric acid would you get? So the mass of nitric acid is given by product of these two over this. So that would be 23.0 gram times 2 times 63.0 gram over 3 times 46.0 gram. Cancel these two units and simplify this to get the mass of nitric acid produced in grams. What do we have next? First generation car airbags were inflated with nitrogen gas released when about so much of sodium azide NaN3 is ignited with a spark in case of accidents. What is the volume of nitrogen produced assuming all sodium azide has decomposed? I will let you attempt this question and figure out the mass of nitrogen produced first. Because using this balanced equation, you can figure out the mass of nitrogen produced from so much of sodium azide, because you can figure out a relationship between the mass of sodium azide and mass of nitrogen from the balanced equation. From that, you can answer this question just the way we did here. Once you have the mass, you know how to calculate the volume given the density of nitrogen. Density is nothing but mass over volume. So volume would be mass over density. You calculate the mass from this relationship and the mass given, then use it to calculate the volume because the density is given.